We'll start with the description of an experiment, and through that we come to a certain concept that we have to study as part of this syllabus. So the first experiment would be this one. So you take a cube of ice, which has been set in this manner. So you have a probe thermometer. Okay, which is basically a thermometer which has a probe in it, and that probe digitally measures and displays the temperature of whatever it is that you kind of poke it into. So you make the ice, obviously, place the probe inside the water, then set it in the freezer, and check the temperature of the freezer as the ice freezes. And naturally, as we all know, ice freezes at a temperature, water freezes at a temperature of 0 degrees Celsius. And then after that, the freezer's temperature will go further down. It might go as low as, let's say, minus 10, minus 12 degrees Celsius. Now you take the ice out and allow the ice to heat up, and then note down the temperature of it. So what you would do is, every couple of minutes or so, you note down the temperature and the time. So you got time there, so you do temperature here. Okay, so serial number 1 times 0, you just took it out of the refrigerator. The temperature of the ice is about minus 12 degree Celsius. Okay, 2 minutes later, you check the temperature, it's about minus 11.5 degrees Celsius. Third reading, 4 minutes down the line, let's say the temperature came to minus 9 degrees Celsius. This depends. The change in temperature, of course, depends upon what your ambient temperature is. Are you in a hot room? Is the ambient temperature high, low? That matters in how it changes. But when you do this, what you will notice is that somewhere down the line, maybe about 16 minutes later, the temperature, let's say, comes down to about 0 degrees Celsius, or maybe 0.5 degrees Celsius, or minus 0.5 degrees Celsius, whatever it may be. And then you'll notice something very curious happening at this point. You'll find that at subsequent intervals of time, the temperature does not vary by much. Okay, so maybe it's uh, 18, and then 20 minutes down the line it's 0 degrees Celsius, and you'll find that for a while this temperature remains 0 degrees Celsius. And you will also find it curiously that during this point of time, um, the water puddle that forms around this ice will start increasing, which obviously means that the ice is melting. And this will remain in this manner until the probe gets exposed to the external temperature. Once that happens, then obviously it's going to rise. Now take that as one experiment. Okay, now let's look at another experiment. Another experiment would be to take water which is at room temperature, let's say 25 degrees Celsius, and then you begin to heat it. You do the same thing, take a probe and um, note down the rise in temperature. In this case, because you are using a Bunsen burner, you will have to note it down at perhaps 1 minute intervals, and you will see the data again in terms of time and temperature. Okay, you note it down at 0 at time t0, 25 degrees Celsius. Second one at time 1 minute, maybe it went up to 27 degrees Celsius because there is heat being applied, so heat being provided, so the temperature of the water will rise. And naturally, as you continue, say, let's say in about 5-6 minutes time, you will find that the temperature has gone up to, let's say, something like about 89 degrees Celsius. Heat it for a little while longer in 7 minutes, maybe it has gone up to 98 degrees Celsius. And then again you notice something curious that will start to happen. The water will of course start to boil at this point of time. So you'll have bubbles rising through. That's what indicates to us generally that the water is boiling. And during this time, for the next subsequent few readings, 8, 9, 10, let's say, the temperature does not change. Okay, so this is something rather curious. When ice is melting from sub-zero temperatures to 0 degrees Celsius, the temperature keeps rising until it comes to 0 degrees Celsius, and at 0 degrees Celsius there is no further rise in the temperature. Similarly, the same thing happens when you boil water. When you heat water from room temperature up to the boiling point, it reaches the boiling point and then refuses to increase further. So what you are observing over here is that while the ice is absorbing the temperature from the surroundings, because it is at 0 degrees Celsius and the surrounding temperature is higher, ambient temperature is around 24-25 degrees Celsius or more, so the heat obviously is still being absorbed. Okay, but there is no registration in the temperature rise. Same thing happening over here. The Bunsen burner is heating, you are using up gas, the water is obviously being provided energy, heat energy, but again the temperature rise does not occur. So this curious phenomena is something that can very easily be observed. And what is happening over here is that if I ask you the question, what is the critical change that is occurring in both these situations where there is no registration in temperature increase, but energy is still being provided, then you'll realize obviously that both these cases there is a phase change involved. Okay, so what is this phase change? You might have studied it in earlier classes. A phase change is a change that occurs when any substance undergoes a transformation from one phase to the other, and the three phases that are there, which we generally deal with in thermodynamics up to this level, in heat up to this level, will be solid, liquid and gaseous state. Okay, there is of course something called as a plasma state, but we are not worried about that at the moment. So when you provide energy, what happens is that the solid phase goes to liquid phase, and if you continue to provide energy, the liquid phase goes into gas phase. Now what seems to be occurring as an observation of these two experiments is that between the change in phase from solid to liquid and from liquid to gas, heat energy is being absorbed by the substance without any change in the temperature of the substance. Okay, and this is what is known as latent heat. Okay, and that brings us to the topic phase change and latent heat. Now what is the explanation for the reason that during phase change there seems to be a latent heat absorption that is taking place, which does not register as a rise in temperature? The reason why we call this as a latent heat is because latent signifying hidden, not apparent, but heat is there. So not apparent or hidden heat. So how do we understand this? One way we could tackle this question is to ask what happens to this heat energy which is provided to the molecules. And to understand that, we go back to the kinetic molecular theory. Okay, what does that state? Just a quick reminder, the kinetic molecular theory states that matter is usually made up of, mostly made up of atoms and molecules, not mostly, almost all, I mean always made of atoms and molecules, and that these atoms and molecules have some amount of internal energy because of which they vibrate about their mean position. Okay, so this vibration is what accounts for the internal energy of the object that it is made up of. Providing heat from external sources or loss of heat from the object to outside increases or decreases the internal energy. So this internal energy or the kinetic energy, the thermal kinetic energy of these molecules is what registers as a temperature change. So when you have a thermometer, a probe thermometer or a liquid in glass thermometer, whatever the case may be, that absorbs the heat energy and then registers the temperature change, right? So obviously what is not happening according to the our understanding of kinetic molecular theory is that the internal energy is definitely not going up, because if the internal energy of the substance is going up during phase change, then a temperature change will be registered. So since that is not happening, we can conclude that the internal energy or the kinetic energy of the molecules is not going up. Then what else is happening? Well, the explanation for this is that this the latent heat that is being provided in both these situations, in the case of the melting ice and the boiling water, the energy is being absorbed, but it is being absorbed to increase the intermolecular distances. Okay, so water molecules, let's say they are like that, something like a Mickey Mouse model, but okay. um, and this is just a kind of a rough and ready explanation, don't think of it as a serious explanation, but there are intermolecular bonds that are there between these atoms which hold them in place together, and these intermolecular forces are what gives the shape of the ice crystals when they form, and it's also what holds the molecules of the water together when they are in the liquid phase. So when phase change is taking place, the latent heat apparently increases the amount of distance between the intermolecular spaces. So what is happening is that their vibration is not increasing, but their distances between the intermolecular spaces are increasing. I shouldn't be really saying intermolecular spaces, because there isn't any volume, significant volume change that is taking place. So it must be stated in a way their potential energy increases. So they are kind of being stretched apart. Okay, but the volume change does not register. If you look at the volume of this, it does not show that there is any great increase in the change in the volume, and that accounts for the latent heat. And once the separation has significantly happened, and that's very clear in the case of the ice, because you will see that the phase change has been completed from ice into water, and then the water molecules start absorbing energy from the ambient conditions, and then from 0 degrees Celsius you will start seeing a rise of temperature uh, further on. Okay. Now the last bit of this is when you do a graph of both these situations, whether it is a increasing temperature of ice melting or boiling of water, there will be a point where the graph plateaus. How that happens, what is latent heat, what is specific latent heat of substances, and what are the significant consequences of this latent heat for water, all this we will see in the next video.